Right then, I'm never sure whether this session is a curse or not because everyone's had the lunch and is probably half asleep right now. But thankfully the room's reasonably cold, so hopefully that'll keep people awake a little bit. But just to introduce myself, my name's Paul Power. I work for a company called Stats. We specialise in sports analytics, and specifically my role is working with soccer data, otherwise known as football in England. And today what I'm presenting to you is some research that our group's been doing, looking at measuring passing quality. So, in terms of what I'm going to present to you today, the first part is to talk about the current issues with existing passing statistics and why they're bad. Then I'm going to describe how we actually solve this by starting to learn context and games-based scenarios. And then actually show how we create the features using spatial temporal models via handcrafted features, using supervised learning by using experts to generate gold standard labels, and then finally by using unsupervised methods as well, so we can learn from unstructured data. And then from that, how do we actually apply this in the real world? Because it's all very well having lovely techniques, but unless the coach can use it and understand it, there's no point. Okay, so just as a show of hands, how many people here are actually soccer fans? Ah, excellent. This is much better than I expected. So, this might actually work now. So, the first thing, I'm not going to do any work for this bit. This is all on you guys, okay? So, I want you to basically tell me which of these two players is better based on some of the statistics I'm going to give you. So, the first statistic is the old classic, the average number of passes made per game. So, player X makes 47.6 passes on average, whereas player Y makes 48.6. The next statistic is the average completion rate. So what's the average percentage of passes successful? So again, X is 83.6%, whereas player Y is slightly better at 84.2%. And the final bit of information we're going to give you, something with a bit more context, is the number of long passes. So player X now actually does 4.8 passes on average, whereas player Y does 3.2. So based on that information alone, can I see a show of hands if you think player X is the better player? Okay, a lot of confidence at the front. Okay, hands up if you think player Y is better. Hands up if you haven't got a clue. Excellent, and that's probably closer to reality. Okay, so these are the current statistics we get. However, if I actually unveil who these players are, suddenly we go, we've got an issue here. So, for those who don't know, the player on the right is Eden Hazard, and he actually won Player of the Year in the Premier League last season, and is one of the preeminent attacking midfielders in the world. On the left is David Luiz, who is a centre-back, who's very good, but was in the Brazilian team that got beat 7-1 by Germany. Okay, so already we need a better measure. So, what's the actual problem? Why is this happening? Well, the issue is that every pass is currently being weighted as a binary event, either 1 for successful or 0 for unsuccessful. However, not all passes are created equal. So to demonstrate this, again, I want you guys to do a bit more work, okay? We're keeping that brain ticking over. So can you rate these passes? So here's pass 1. Okay, is it right? I don't know if we can do anything about that at the back. Yeah, I've increased it on my side, yeah. So I'll try and play that one again. Hopefully you can see this. There we go. So some predictive analytics straight away here. Where's the ball? That's a great one. Talk over. Okay. Right then. So there the ball basically went from the centre circle out wide. So that was quite a simple pass. This is the next one. So this is going to be a long ball through the middle. Okay. Then, sorry? Where did the ball end up on the second one? So it ended up just on the edge. I don't know if there's any way if we can. Yeah. So let me just play that one again. So you'll see it go along the ground, and it's being flicked up in the air. Okay, perfect. So what would you say? Good pass, bad pass, indifferent, risky, come see, come sa? Okay. Okay, so then we have the third pass. which is a little ball around the corner in the penalty area. Again, I apologize for the video screen. And then we have our final pass. So this is a long ball going in the opposite direction. That should finish on the edge of the penalty area. Right. Oh, listen to that already. Oh, geez. But this is soccer. This is sport. We use words to describe what we see. It's very much about feelings. And this is the issue. With a 1 and a 0, you can't capture that. So for us, we want to be able to capture this language. And there's 2 parts to a pass. The first element is the risk. So what's the chance of a pass being intercepted? The second part then is the reward. So what's the chance of a shot resulting from it? Okay. So how can we measure this? Well, what we could do is we could go and consult an oracle, particularly a fantastic manager like Jurgen Klopp. I'm a Liverpool fan. However, the issue is that you show the same person, the same 3 different people, the same pass, they're all going to have a different version of quality. So we need an objective measure. So this is the problem we have. Given a large amount of tracking and event data, i.e. where is the ball, and event labels, can we objectively and accurately model the risk and reward of a pass? This is what we need to do. However, there's problems. The first problem is that sports data is highly unstructured. Players are moving all over the shop. People are constantly changing roles. So as a result, it's non-linear. In addition to that, by the way, this was actually voted the worst passage of football for the last 20 years. This is my team, how I play. But this is the reality. It's highly unstructured, so it's non-linear. But in addition to that, it has to be context-specific. You have to understand, are we playing in chaos? Or actually, are we in a structured play? And then finally, and most importantly, it needs to be interpretable. If you present something to a coach, and they ask you, how did you get to that number, and you can't explain it, they're never going to use it again. So this is the real world of data analytics. So how can we solve this? The way we solve this is we take the approach of creating a dictionary. So initially what we have is a set of raw data variables, raw data values, which includes the player trajectories, which is in X and Y, and is sampled at 10 Hertz, so once every 10 seconds. We then have the ball data, which is basically interpolated based on where the players touched the ball, and then from that we generate labels. So is it a pass? Is it a cross? Was it successful or not? Okay? So that's the first level of data. What we then do is we handcraft what we call micro features. And you can think of these as key coaching points. So this is then when we speak to our oracles, our experts, and ask them, what is it you think actually influences the model? So in this case, we look at the speed of players. Is a defender applying pressure to an attacker? What's the passing window? So what's the space for the player to actually play the ball in between? Simple stuff that anyone can craft. Then we move more into a supervised element where we start to identify tactical features. So are you in a counter-attack? Are you in a build-up? And then finally, we start to use unsupervised learning to actually understand formations from the tracking data. And not just that, we can start to generate specific coaching labels. So is a team in a high block, a mid block, or a low block? So from this then creates a feature space. So we're basically taking this nonlinear data and linearizing it, okay? And then as a result, we just put it into something simple like logistic regression. Now we could use something like a random decision forest. However, when the coach comes back to you and says, what's the influence of pressure on my player losing the ball? We don't know. So the beauty is, because we get given these coefficients for each variable, these coefficients act as coaching points. So you can now use that. If it's a positive correlation, they know, hey, we need to work on this. This is actually going to be a benefit for us. So that's why we've used this more simple model. Okay, so how are we creating the data points? So in terms of the micro, and I should say, we do have some papers on this as well that we've already looked at. So the first thing that we have to solve is, who's the pass actually intended for? So you might have a situation where you have two players looking to pass the ball. The ball then gets played forward, but then the defender intercepts it, okay? But we all know with our eyes, that pass was intended for the player on the right, okay? But the computer doesn't know that, so we have to teach it. Now, to do this, we just use actually a very simple method. Initially building on work by Michael et al. In 2015. they used a simple approach where they just basically took the nearest angle to the line of the pass, and whoever was nearest, they said that was the most likely intended passer. But the issue with this is that if you have an attacker actually closer to the passer, he gets identified, so it's not perfect. So all we do, and this is just a rough method to get us going, is that we add in a distance threshold as well. So if you're the closest player distance-wise and angle-wise, the chances are that you're probably going to receive it. Now, we could have built a probabilistic model, but we've looked at this historically using conditional random fields, and we actually get 68% accuracy in terms of predicting who's going to get the ball next. So this method actually works really nicely to just generate some basic labels. So the beauty is, now we can start to identify who we think a pass was probably intended for. We can start to actually craft some of these features that the coaches want. So for example, the first one, because we know who's probably going to receive the ball, we can identify how much pressure is that player under. The next thing that we could then look at is, well, what's the actual window that this player's got to pass the ball in between? And also, what's the pressure towards the passing line? And then finally, we can start to incorporate stuff like, was it a first-time pass or not? And again, because we know who the pass was intended for, what's the pressure being applied to that player? So after this, we then go into our supervised learning. So within this, we worked with a set of coaches to start to identify specific styles of play that they would define. So in this example, there's something called direct play, and direct play is basically passing the ball vertically a long distance. So with this, we kind of have a membership value. You can think of this as a probability. So as the distance increases, the pass goes longer, the higher the chances that's going to be a direct play style. The next one we then look at, for example, is counterattacks. So a counterattack you can think of as a transition. So when the team win the ball, how quickly do they then move that ball forward into the attacking zone? So again, we identify this through the data. We have a model that then says, is it a counterattack, yes or no? And then actually, how strong is that counterattack based on the speed and the distance the ball's been transferred? And then finally, we start to look at possession styles, which for this, we've grouped all these together as one label called build-up. So the first part looks at maintenance. So where you actually have the ball in your own area. The next part, then, if I skip this along, is sustained threat. So your ability to keep the ball in the attacking area, in the final third. And then finally, if I keep on skipping, we have something called build-up, where you're looking to basically play the ball from your own half and passing the ball between the lines. So this now generates a new set of labels so we can capture the context and also the time dynamics of what's been happening previously. And already we've actually been using this to identify like the play style philosophy of teams, and this has been really nicely used in the media to identify how teams might play. In addition to that, we can then also break this down at a player level. So what we can start to do is look at, if you're buying a player from one team, what might he start to produce for your team when you drop him in based on your style of play? So the final element that we look to build in is what we call our formation features, and this is where the unsupervised learning comes in. And this is something our research group has really had a big focus on. The main reason for that is football data and any sports data with tracking is really, really messy. So what we want to do is to find the underlying structure. So for example, if I just plotted everyone's trajectories over a game, it basically looks like I've given my two twins a load of crayons and asked them to go crazy on the fridge. Okay? It means nothing. It's a mess. So what we then need to be able to do is to transform the data into something that starts to look a bit more understandable. And this is basically a minimum entropy exercise. So what we can start to see here is as we start to minimize the entropy, we start to get this underlying structure. And with this, in terms of a football expert, we can label this a 4, 2, 3, 1. But you already knew that, didn't you? You know, it's obvious. So this now generates a template. So now that we've actually got a formational template, what we can actually start to do is look at, okay, this is actually where the players are. This is my template. Can I now actually align these two over each other and start to assign a role to a player? So what is he actually occupying? And to do this, we basically use simple linear assignment. So we have our input vectors, which is the players' x and y's. We then have our template, and all that we're looking to do here is to minimize the distance between each player and each role. And then from that, once we get a cost matrix, we use the Hungarian algorithm to make our assignment. okay? And then as a result, we can then start to say what role is each player actually occupying. So from that, this now allows us to do our clustering, and we can start to identify different formations on how teams will play. But not only that, we can start to learn a new dictionary in terms of defensive structure or attacking structure. So in this case, this is really popular in terms of football terminology. On the top, we have something called a high block. And a high block is basically when the attacking team or the defending team are really pushing up high into the opposition's half. We then have a low block where you're defending your own penalty area. And then we have a mid block, which is in the middle of the pitch. So as a result, we can now generate these labels automatically every frame. So here we have a low block, and we can see here the red team are very compact. They're defending their own goal line. And this is really important labels, because to try and break down a low block is really difficult. And as we can see there, they're being forced into a difficult pass, which the defenders have been able to take. So just having these labels helps us do better prediction. Well, we think it does anyway. So this is what we've done. What were the results? So to actually get, a baseline, what we want to understand is, on average, how often is a pass completed? So to throw it out there, what do you think is the average passing percentage? Can anyone have a guess? 80%. So 80? Anyone higher? Lower? 50? Okay. Wow, you don't think players are very good. All over. Yeah. Right. The actual average completion rate is 84.75%. So interestingly, players are actually pretty good. I mean, you'd hope so. These guys are getting paid. So this is our baseline model that we want to beat. But just to show you, when we start adding in context, we see that the percentages change. So passing forward is a lot more difficult than passing backwards. The same as the length. Going long is more difficult than passing short. And then finally, the type of pass. Is it first time? Is it final third? Or is it a penalty area? So this gives us our baseline model that we need to beat. So how did we do? Well, what we can see is we have that baseline. And in terms of classification rate, as you'd expect, because you're treating every pass as having an 85% chance of probability being completed, we get 85% classification rate. So that's simple. But as we can see now, as we add in the different levels of context, we start to get really, really good recall. And it's when we combine all these features together, this is when we get the best bump. So what's interesting, just adding in the tracking alone doesn't really do anything in terms of improving performance. You have to teach the computer these different latent factors. So that's in terms of classification, but what in terms of model performance with log loss? So interestingly, while just using the baseline number is quite good in terms of classification, it's basically noise. You know what I mean? It's very random in terms of how it assigns it. So again, we can see that once we add in all these features, this is where we really get our best performance. So that's what we've done, but how can we actually use this? That's what this is all about. Well, going back to our examples where we couldn't see them before, what we can now do is we can actually start to rate these situations. So this pass was a low risk with low reward. This next one was actually quite a risky pass. As you can see, the ball's given away with a medium reward. This next pass was actually a medium risk, but quite a high reward. And then the final Gasper one that we had, this is the highest risk. So there's basically a 62% chance of that pass being intercepted, but there's basically a 1 in 4 chance that there's going to be a shot, which still feels quite low, but that's actually what football's like. It's really hard to get shots off. So once we've done that, we can actually aggregate these values together and assess the players. So these are actually from the 2015-16 season, the top 20 passers in the league. And what we do is we look at passes added. So for example, if I have a pass that's got a 50% chance of being completed, and I complete it, I get 0.5 added onto my score. Simple as that. If I don't complete it, I have 0.5 taken off. So we can see here that all these guys are basically adding passes to their team. And interestingly, we have basically all the best midfielders here in the league for that season. But what's really interesting is we start to highlight some centre-backs. And centre-backs are normally derided for their passing quality. But we've actually got some guys here who are pretty exceptional at passing. The other thing we can start to do is say, okay, so these are the best passers, but who's actually making the really dangerous ones? So again, unsurprisingly, we have our elite players like David Silva, Mesut Ozil, Kevin De Bruyne, but we have this standout player called Wesley Hoolahan. Now, why this guy is interesting is because he played for Norwich City, and in this season, Norwich City got relegated. Yet we've got an elite attacking midfielder. So, if I'm wanting to recruit a player, this is who I'm going to buy. He's going to be at a lower price, so can I go and get that player? The other thing we can then do is post-match. So, for example, in the media, on the left, this is a typical stat, who's made the most passes. But on the right, we can actually now say, well, who's actually made the most dangerous passes? This, as a fan, is what I want to know. Finally, we can actually start to get into some coaching application. So in this case, because we've learned the dictionary, we've generated language. So I can now use that language. So in this case, has Eden Hazard made a pass against a high block that's led to a shot? Okay, so we can now get these search terms. And then finally, because I think time's about to be cut out, we've got personalization. So now, rather than us telling you that you've made a long pass, coaches don't want to know that. They want to define something for themselves. So because we learn the underlying structure by the way we can do role alignment, they can say, this is how we play. So this is the Mourinho switch play. And we can automatically detect every time that's happened. You can go on, you can click it, you can give this your own label, and then as a result, you can now automatically update this for how many times that's happened. Okay? So to summarize, we've created a better way to measure passing quality. We've done this by creating a feature set which is capable of capturing the dynamic interactions between sets of players. But most importantly, we've got a model that's interpretable. Coaches can understand it and trust it. And then finally, we're now able to advance the application of passing statistics in player recruitment, match analysis, and also evidence-based coaching. Right, thank you very much for listening.
So thank you very much for the very